And we're in lecture now. Something interesting from homework that I wanted to go over with you, and something from a student. And remember, I asked you to write something interesting that you observed or were able to show or spotted in the assignment, and I mentioned some of them on Thursday when I worked it out with you. I wasn't really looking for the diagrams. I mean, I figured, everybody was going to have a plot like this. Charge 1 and charge 2 and field point H right in the middle, and, and then maybe another diagram with the field point and then the constituent fields E1 and E2 like that. Same size. I noticed one student did have a diagram a little bit like that, except his arrows weren't the right size, but his writing was right on the money. His writing indicated he knew that the arrows were the same size. So I said, all right, your sketch is a little shaky, but your description tells the tale. So I didn't take any points off from him. But anyways, this is kind of, and a lot of you had stuff like this. Some of you tried to have stuff like this and messed up a little bit. But this, nobody had except one person who is not here today. He wrote the field lines of this double, this is not really a dipole, it's a double positive array. And he wrote, actually I can quote it. He's still in the pile here. I just loved what he wrote because it was, and I especially loved his diagram. Somewhere in here. Find it later. Yeah, the student was thinking in terms of the field lines and this array of the field lines. And the student made the decision, there's no field lines that ever get to point H in the middle. They're all kind of evading point H. And this is a diagram from the textbook. And he must have been looking at this. And we talked about this one in lecture too. So he said, okay, field line intensity 0, electric field is 0. They're so sparse, you can't even write one field line in there. And that, my wonderful students, is wonderful to behold, because that is thinking outside of the box. Just like this famous guy for NASA, John Aaron. This is the guy that figured out the critical move in Apollo 13 that brought those 3 men safely back to Earth, way back in the Apollo program. Very famous engineer. They call him the steely-eyed missile man. And this student, boy, they earned their spurs with this homework. And I completely did not expect it. And therefore, I'm very happy. And when that student does show up, I'll shake their hand. So I just want you to know that I am trying to observe very carefully the things that you produce. All right? And I'm trying to write questions that allow you to state things and, I don't think of it this way, but state things in a way that'll surprise me, like this. This diagram completely surprised me. But it's completely appropriate for the electric field. Because, it doesn't really, you could say stuff about the potential, I guess, but you know what that looks like. You know what raise your hand if you've ever been skiing, snow skiing. Anybody in here? In snow skiing, which snow is this crystalline form of water that falls on mountains up north, and then you ski down it and stuff. Kind of like water skiing. Anyways, it is water skiing. In skiing, there's a thing called the fall line. In geology, there's a thing called the fall line. F-A-L-L-L-I-N-E. And it's the line that if you take like a ball, a big it doesn't matter to me if you pass the class. So you go ahead and keep talking. And don't pay attention to what I'm saying. All right, you're perfect. This school is 100% voluntary. And so are grades. The fall line is the line down a hill or the side of a mountain that a skier, if he wants to have maximum speed, he follows that line. Now, if you're on a perfectly conical hill, which doesn't exist, but it's straight down and equal, like pickup sticks, like a tent made of pickup sticks. The fall lines are all straight down. But if you're on a regular mountain, the fall line can go in different, curves and stuff. But that's what we have here. The electric field lines are like fall lines on a mountain for which the height is the potential. Let me repeat that. The electric field lines are like the fall line on a mountain for which the altitude is the potential. We looked at that potential. We looked at one of the profiles of that mountain last Thursday when I showed you this, or Monday, I guess, when I showed you the solution for it. It's flat. It bottoms out at x equals 0. And then it spikes upward. That's the mountain. There's two peaks here. One peak at the positive charge on the left, one peak at the positive charge on the right. And guess where the plateau is? Between the tableland, between the two mountains, right at field point H. So you can talk about field lines. You can also talk about potential, because these field lines tell you the fastest way down the mountain. If you think of the voltage, the potential as being a mountain. All right. Now I want to, that's my comments about the homework. Office hours tomorrow after lunch and before lecture. That's kind of an informal time. And you can drop in any time for any amount of time. So if you can only make, 20 minutes at, 1 o'clock to 1:20, and then you got to bolt, that's all right. You just drop in, and hopefully you'll get to ask a question if there's not too many people. If there's a ton of people, you might have to wait your turn. But that's all right. That's the normal method. Room 158, PS 158 in the Physical Sciences building. There's the picture of it. We've already looked at that once. It's right by the main entrance. So go in the main entrance and then turn left. It's the first door. And bring your agenda. I don't really have an agenda for office hours. If nobody comes, I'm doing grading and other stuff. I have my own office work to do. But if you come, we'll do whatever you want to do. whether that's talk about an exam question, something about your grade, homework, anything like that. Now, we're going to have written homework tonight. I'm going to publish it at about 9 o'clock, sooner, hopefully, about the stuff that we talk about today from Chapter 21. And so tomorrow would be a good time to talk about Chapter 21, the written homework. So you might want to talk about that tomorrow. Now, the times are informal, so I'll try to get there about 12:30 p.m., maybe a little earlier, and then we'll dismiss and everybody mosey over here to the lecture hall at about 2:30 or so. All right? Any questions about that? Was that a question? I saw you raising your arm like this, like you were, oh, okay. Okay. Oh, question? Do you have a question? Okay. Let's talk about forces on moving charges. We talked about this yesterday, and I have some very specific examples to work out with you. We're going to work on the computer screen from Apple Keynote, and we're also going to work in the document cam. But let's start with the basics. This is the diagram from the textbook about the right-hand rule for forces on an object. Force is in blue, magnetic field is in red, and the velocity, it looks like it's purple, kind of purpley. And what they say is make your thumb go in the direction of V and your fingers in the direction of B, and then your palm is facing the direction of the force, F. Now, that is completely different from what I taught you on Monday, but they're completely equivalent. So you go with the one that I taught you, go with this one. I don't know, there might be some other way of expressing it, but always using your right hand. Now, I want to point something out to you. You're going to be using the right-hand rule today in a few minutes. We're going to do some clicking questions. Make sure you, let me start the clicker. Hold on a second. You get your clickers out, and I'll get my clicker out here, and we'll start clicking. Okay. All right. As I mentioned, we're going to use the right-hand rule, and I want to mention something about it to you. It's tricky, and matter of fact, I made a mistake with the right-hand rule yesterday, and it's always it's tough. It's tough to draw on paper with the right-hand rule, and that's basically what happened to me yesterday. I corrected it on the PDF that I posted last night, so I added some more notes on the PDF, so it's a little extra instruction on that. But it's very tricky, and I had a memorable experience when I was in grad school. I was studying for in the school that I went to, what they call the qualifying exam. Okay, and that's whether you qualify to get a master's degree or whether you qualify to try out for the PhD program. And then after if you do qualify for the PhD program, then you got to take the PhD written exam, and that's even tougher. But anyway, so I'm studying for this qualifying exam and just going over basic physics, kind of like a lot of you seniors are doing, going over physics 1 and 2, basic physics, to get ready for MCAT. So that's what we were doing, getting ready for the qualifying exam. And I was working with this book, and I was going through a chapter of magnetism problems, and I kept getting the wrong answer. I kept getting the velocity backwards from what the, because they had the answer written down, or the magnetic field. And so I'm writing all this stuff, and what I found myself doing was I was using my left hand to do right hand rule, and that's why everything came out backwards. And I'm mentioning that to remind you that it's, when you're concentrating on an exam, I have seen students using the alternate right hand on a magnetism problem. And it is the only situation in which I will actually help a student on a test. I will see a student going like this and trying to get it right and whatnot. And I'll tell them, no, use your other right hand. Okay? So if I see, hopefully you guys won't be like me and use the left hand. But if you do, if I see it, I'll try to gently remind you. Anyways, it's tricky. But the thing that's important for us and that we talked about last time is that the magnetic force gives rise to a centripetal force and a circular or spiraling motion. Now, we're going to go through two situations here today, two examples in detail, in which the magnetic force is balanced and in which the magnetic force is unbalanced. So the first one we're going to do is the balanced example. So go ahead and draw yourself a sketch with a uniform magnetic field, like what I've got here. Okay, and this one, the X means that the magnetic field is going into the board. Okay, it's going into the page of your notes. And those X's representing the back end of an arrow that's moving away from you, i.e. into the screen, into your paper, those X's are uniformly distributed in my sketch. Now, the textbook just puts little X's. They don't put a little circle around it. And they make them kind of small. That's all right. I want to make sure these are nice and big. Now, we've got a positive charge, undetermined size, moving in from the left side and heading to the right. So my V cross B, okay, the Dr. Brickner right-hand rule, V cross B. So I want you to think about how that right-hand rule is going to go. All right, now I'm going to clear out this diagram a little bit, and I'm going to replace all those X's everywhere because I need the room with just this symbol. All right, so when you see me write a magnetic field vector and a single circle with an X in it, or a single circle with a dot in the middle of it, then that means uniform. Okay? And we're just trying not to clutter up the diagram. Although the diagrams in the textbook are pretty nice, and we're going to use one in a second. All right? So here's our situation. Now, I'm going to ask you a clicker question. All right, so get your thinking caps on. All right, and here I've got the same diagram up. All right. Question. What is the direction of the magnetic force on this positive charge in this magnetic field? All right, this is basic right-hand rule territory. Try not to sprain your wrist. And definitely consult with your neighbor and stuff. Okay? Are you coming up to see me after class? Yeah. Yeah. Didn't you message me? Yeah. Are you coming up after class? Okay. No, not the left hand. Put that hand down. That's the one. This one. 30 seconds to make your decision. This is very, very lovely to see you guys working on this, thinking things over. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Let me see what you guys voted for. Oh my goodness. You guys are geniuses. Most of you got it. A couple of you got tripped up. Yeah, if you got tripped up, look, right hand rule is good for this one. Okay, the right hand goes in the direction of the velocity. It curls into the page to get to the B. You know, so it curls around like this. And then my thumb points the direction of the force. All right, now you can use that Dipsy version of it in the textbook, but I'm not going to use that. Question?
Can you shoot a little bit slower?
What?
Can you want to make your hand thing a little bit slower?
Okay, first, I use this right hand. I point my fingertips in the way of the velocity. And then, see now, if the magnetic field were out of the board, look, if the magnetic field were out of the board, I'd have to go like this in order to curve my fingers that way. So, you know, if the magnetic field is like this. But this magnetic field's in, so I go like this, fingertips in the direction of the... This is great to see you guys imitating my motion here. So fingers along the velocity, and then I curl around to get to the magnetic field in my thumb. You can only curl around this way if your thumb is up in this direction. All right? If you're using your right hand. Okay? And hey, you guys, if you got tripped up on that one, we're going to keep practicing it. We're going to get it. It's just, you know, it needs practice and looking at different variations and stuff. And you're probably going to have some lab. What did you guys do in lab this week? Batteries and bulbs? No magnets, no coils yet. You'll do coils next week probably. In yellow. No. You're using this to figure out the force. Okay? Now it's in the Dr. B method, and the way that many people use right hand rule, your thumb is going to be the force. Okay? So it's either going to be like this. If your V is this way, your force is going to be, you know, somewhere here, you know. But you've got to be able to curl your fingers into the board like this. See this?
What would you do if you wanted to go down? What scenario would cause you to do this?
Another question with the magnet, and I mentioned it already, if the magnetic field were coming out of the board, so that'd be a circle with a dot in it. Then I'd go like this. Okay, and then my magnetic field is going that way, so I got to curl my fingers this way. And I can't do that with my right hand unless my thumb is pointing downward, and then I got a downward force. No, it's just, you can't say that. I know you want to have a simple rule in, out, but it's not. You got to pay attention to two things: the velocity vector and the magnetic field. You know, and this is, and think about doing this in 3 dimensions. You know, up in the upper atmosphere where the aurora borealis is. That's where they really do a lot of this stuff. But it just requires, you know, practice, and we'll get it. We'll try to practice. Another question. Yes, in the back.
So if you were to do this with the rule that you showed us, like
Well, the force,
It was really weird with the. I tried the other one to see it. It was in the same axis.
yeah, you know what? I don't even want to go back to that.
Fair enough.
I mean, because I've never seen it outside this book, actually. But the thing is, if you go on the internet and type in right-hand rule and then like magnet or magnetic field, you'll see like zillions of diagrams, zillions of YouTubes, and I have never once seen the way that people that it's in the textbook. But it's equivalent. I mean, you could go back and figure it out. It's equivalent. But I like this one. Now, so this is a magnetic field. Positive. So here we go. We're looking at the force on a positive charge moving to the right, left or right, and a magnetic field that's going into the board. All right, everything's copacetic. We can set this up. We get a horseshoe magnet. A horseshoe magnet is a nice kind of a magnet. The reason they make them is because if you make a horseshoe magnet, let me draw a picture. Get rid of the circuit. If you make a horseshoe magnet, a horseshoe magnet in grade school looks like this. When you're playing, screwing around with stuff. But in the lab, a horseshoe magnet is extremely huge, but it's still a horseshoe magnet, but it's more like a D magnet. It looks like this. And right in here is the uniform part of the magnetic field. Now this is not uniform down here, but in between the poles, so one of them is the N and one's the S. Right in between those poles, that's where you put your experimental device and get magnetic effects. And then, they have other electromagnets that are similar to that, where you get a nice uniform field. But anyways, all right, so we got the force. And by the way, this one gives rise to the centripetal force that we're going to talk about a little later. Okay, well, first we got to do one extra thing. How do you balance a magnetic force? Well, one way you can balance it is with parallel charged plates. That's what we're going to do now. All right, so maybe make another diagram, make it big and nice, so you can sketch in all the fields and stuff. Here we go. Put the parallel plates top and bottom so that this particle goes right down the middle. Okay, so parallel plate above, parallel plate below. All right, and we know that, go ahead and sketch in your field lines. Good set of parallel plates. Ideally, it will look like this. All right? Uniform out till you get about to the, last few centimeters out by the edge. But we'll just kind of idealize it here. Nice uniform electric field. A horseshoe magnet, nice uniform magnetic field. Where else you get a fairly nice uniform magnetic field is two bar magnets that are held close together. A north and a south poles held together. It works out nice. So, I'm going to ask you a question. All right. And notice I haven't told you anything about which plate is positive and which plate is negative. All right? So I'm about to ask you another clicker question. And this one is right here. Which one should be positive if you want to get a downward? I mean, magnetic is up. We got that. All right, it's radiant rule. Now, how do you get something to balance it with a downward, some downward newtons? Which one do you make positive? Which one do you make negative? So answer the first one. Which one do you make positive? You don't need the right-hand rule for this. Just got to remember, I've even drawn in the electric field lines. But which direction do they go? Okay, 1 minute. And yeah, talk it over with your neighbor and kind of work out a concept. Twenty seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Wow, you guys are geniuses. Yeah, top plate. Top plate is the answer here. Yeah, you want the field lines to be going downward, and that's the way a positive charge is going to get pushed. That's what field lines tell you. No matter what size the particle is, if it's a proton or if it's positive 5 coulombs, it's going to get pushed downward. So let's look at the forces now. All right, if we set them equal in this system where we have everything at right angles, at least at this snapshot in time, if we say that if we want the system to equal, then we have to make QVB equal to QE. Question here in the third row.
Going back to the diagram that I fixed, we both said the positive, but for different reasons. I just don't know which reason was correct. Is it that the positives are repelling it, that the flow is positive to negative?
Yeah, you could say that the positive plate will repel a positive particle that's trying to go through there, and it'll dip it downward. It'll accelerate it downward. If you shoot an electron through there, it'll dip upwards. Okay. So that's good. Yeah, so I mean, you're thinking in terms of forces, and the electric field is the analog. It's the abstract analog of the force. So you're good. So here's your. Let me move this up out of the way here. Yeah, QVB equals Q. Now, you can cancel out factor of Q there, all right? And when you do, you get this left over and get V by itself. And what this tells you, this is the condition for dynamic equilibrium. In other words, all the forces balance, and we're ignoring gravity. Because gravity is so much weaker than electrical forces that we're not even going to bother with gravity. So this is a condition of dynamical equilibrium, magnetic upward force balanced by the downward electric force of the parallel plates. And what this tells you is that at this precise velocity, the forces balance, and the particle just goes straight down the pipe. If forces balance, there's no acceleration. Forward, backwards, left or right, up or down. If F equals 0, if F net is 0, ding, acceleration is 0. Excuse me. So whatever velocity you enter that area with, you're going to carry it through the area. All right, so now this is a device called the Velocity Selector, and it's mentioned in your chapter 21. Now, what we're going to do now, what we're going to do after the break is work out an example of this on the document cam. So take a 5-minute break. We'll come back at 3:50 and crank our way through. All right, let's keep going. Now, we just worked out an example on the document cam of the Velocity Selector. And we have a question from the back. Did you move to the other side? Did you move to that side at the break? Oh, okay. Question? Oh, God, I thought you were saying, this is section B001 of Physics 2054. The section, I don't know what it is. But it's the Velocity Selector. It's like, actually, I do have it written down. It's conceptual example number 2. And I think that's in it's not the first, and I don't think it's in the second, but I think it might be in the third, 21.3. You can look it up, conceptual example 2. Anyways, I want to go and do another example with you, but before we do that, we have to work now with centripetal. We're going to do a little centripetal force review, a little mini review. Because we're going to do, we're going to try to work out some details of what happens in a device in the laboratory where you're not trying to balance it out with parallel plates. What if you just crank on the magnetic field and then watch that baby curve in a circular motion? Yeah, we want to do that sometimes too. All right? So here's your circle. Go ahead and draw a circle, radius R. And I put my object at point P. So the velocity, and so we're going counterclockwise on this circle. And so Diamante, the velocity vector at point P is straight up. I'm just practicing names. It's good to know names, always. So the velocity vector is straight up. All right? Now, let me park this radius out here. Because now the centripetal force vector is centripetal. And I'm moving that R out of the way because here's the big purple centripetal force vector. All right? It's perpendicular to the velocity, and if it's uniform circular motion, constant speed, constant radius, the centripetal force always points towards the center. And when you're turning, a corner out there on Alafaya, and hopefully at a speed less than 20 miles an hour, from Alafaya onto University, and I hope you're not I know that you are all very nice young men and women. You don't drive like maniacs. Although I have seen many maniacs heading west at about this time of day on University, driving like crazy people from another planet. But anyways, when you're taking a turn, your tires are basically applying, or actually it's the pavement that's applying a centripetal force to your tires, and then it communicates all the way to your car, and it moves your car around the turn. So it doesn't have to be a perfectly circular orbit, but perfectly circular orbit is easy to study. All right, now, here's the formula. F equals mv squared over r. Hopefully you remember that. And so now what we're going to do is we're going to say, all right, my QVB magnetic force, Q times velocity times speed V times magnetic field B, I'm going to say, all right, that's my centripetal force, and I don't have anything balancing, so I'm just going to let it curve, whatever direction it goes. All right, so here's F equals MA. MA is on the left, and F is on the right, QVB. The source of the MA is the magnetic field and a moving charge, QVB. So let me move this over to the left a little bit. And if you get R by itself in this equation, you know, do a little algebra, flip-flops and stuff, you can get and then cancel a factor of V top and bottom. You get this equation that R is equal to MV over QB. Now, I told you earlier that the speed of light is very mysterious. I shouldn't say it's mysterious, but it's very profound. I can look at that and think to myself, all right, Q times a magnetic field divided into a momentum. MV is a momentum. Now, Q times an electric field would be newtons. But Q times a magnetic field is not. And in the numerator is a momentum, MV. And guess what a force is? A force is delta MV over delta T, the time rate of change of the momentum, delta P over delta T. So I'm looking at this over here, and I don't see any T's in there. But you know what I see on the left-hand side? A spatial component, R. And I think to myself, spatial, temporal, speed of light. See, because to switch from a spatial to a temporal component in space-time, all you do is multiply by the speed of light, c. Multiply c times the time, and you get a distance, a temporal component. So I look at this and I think, why is a magnetic field times a charge? I mean, they don't really go together. An electric field times a charge go together normally. That's a force. Why does that go in with a momentum? You know, so it's something, and this is a simple problem. But now, on this, and we're just, you know, we're finished dreaming now. Let's get back down to brass tacks. Get back into the lab. The radius of the turn depends on a bunch of things: the mass of the object, its charge, its speed. Or you could say, instead of mass and speed, you could say it's momentum. And it depends on the strength of the magnetic field. All right? So if you're looking at something and you can measure the radius of it, that will allow you to backtrack and maybe figure out the momentum, or maybe figure out the speed, or maybe figure out the magnetic field. So or maybe the mass of the object, if you can, you know, kind of measure the radius. Because a radius is something that, you know, you can measure. I mean, if you can, like, take a strobe photo of your charged particle going through that circle, then, you know, a couple strobe photos, you can figure, all right, that's about a radius of, you know, 2.5 nanometers or whatever it happens to be. All right? Now, here's our question, and we're going to answer this on the document cam. How can we make use of that circling motion and this equation? All right? And what we're going to do is another example on the document cam together. So here we go. Let me pause. So this document camera exercise about the mass spectrometer and how it works, I want you to think about your diagram. Okay, now this next question is not multiple choice. It's going to be a short answer. Okay, so you're going to have to think of a word, 2 words. And actually, I'm going to give it, let me give this to you. I already have it made up on the document can. So let's talk about this. Or I have it made up in my notebook. So we're going to do this off the document can. All right, so here's my device. Let me back up a little bit here. All right, so here's the device that we just looked at. And we figured out the radius for this circle. Okay, and I said, yeah, you would want to put your collection, if you figure out R, you can figure out where to put your collection bucket. All right, but you know, you might have a bucket up here and a bucket down here. You know, here are the specs that we worked with, 6.3 times 10 to the 5 meters per second. So what I want you to do, here's your clicker question. Describe the state of motion for a positive particle, same charge, 1.602 times 10 to the minus 19, that lands in the upper bucket. In other words, what would be the dynamical characteristics of something that lands up there? And I want you to think about it. Talk to your neighbors and talk it over. You can use that diagram and the one on the board. Describe the state of motion for a positive particle. And what I want you to do, I'll start the, oh, you know what? Before you do anything else, hit the refresh key. That'll switch you from multiple choice over to short answer. Okay, the short answer is going. Type in, so use the up and down arrow keys to select letters. And there's actually a space in there too, so you can type 2 words if they're not too long. I think the limit is 14 characters. So see if you can type in some little short description that describes the dynamic state, the dynamical state, the state of motion, for something that goes into the upper bucket. All right. So you have a mass spectrometer. You might have buckets all up and down that wall, and you measure whatever comes into each bucket, and that might tell you what you got. You know, identify the unknown substance. It's up to you. You figure out what you think is a good answer, and then try to type it in short enough, you know, question. It'll be uniform circular motion, but a different radius. I just gave it away. Yeah, so click in 1 or 2 words and then hit the send key. Don't type IDK. Try it. Think. I'm not just doing this for busy work. I want you to think. And try to spell correctly. I see some more creative spellings, but that's all right. One minute. Written homework will be due Thursday, as always. I'll publish it at 9 o'clock tonight, if not sooner. We're not done with class, though. You're not dismissed. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. You know, we got a million answers here. But you know how you get in the upper bucket? The way to get into the upper bucket is by being slower. No, wait a minute. The way to get in the upper bucket is by being faster. Faster. Because think of it, just think of the formula. The radius is equal to mv. The radius is equal to mv over qb. So if everything else is the same, if v is bigger, r is bigger. The upper bucket is a bigger r, so that corresponds. So it's harder for it to make the turn in that magnetic field. Now, I told you that in the book that's known as a mass spectrometer, but historically speaking, one of the first big places where they used this technology was Oak Ridge, Tennessee, in the Manhattan Project. This is called a Calutron. And these ladies here, you know what they're doing? They're adjusting the voltage, making sure it's nice and steady. Here's a picture of the Calutron, a big, and what they did, how do you get something faster? Same potential difference, but it's faster? Will only happen if it's lighter. And in the Manhattan Project, what they were trying to do was separate uranium-235 atoms from uranium-238. Uranium-238 was a little bit heavier, 238, so therefore a little bit slower, a little bit tighter of a curve. 235, a little bit bigger of a curve. And that's what they did. That's how they got it. That's how they refined the uranium back in the Manhattan Project. Okay, 4:50, now you're dismissed. Look for the written homework about 9 o'clock, if not sooner, you're dismissed.